This is part 2 of lecture 7, and we will continue on the convolution stuff, basically how to deal with images. And in the previous part, on this two-dimensional convolution slides, I have some typos. So last year I used TT prime, and this year I'm going to change it to SNT so that it's consistent. But this is fixed in the slides that I will be posting, so you should be okay. And another thing I want to talk about is I call these things activations. So it's not great because right now we're not talking about convolutional neural networks, so there's no idea what activation is here. So we are going to call it new feature for now. And what we're doing here is basically we have the original images, which are basically pixel intensity features, and we convolve them with some kind of filter that we know, and then we get the new features. And we're going to use these new features to classify stuff in the image. So that's what we're doing here this time. Next time, we will go back to use X as features, and then these A's will actually be the activation in the first layer. But not now. So let's skip these. We talked about this in the previous part already. And let's move on to talking about some specific filters that we can use for specific purposes. So one thing that we want to use filters for is to compute the image gradient. So image gradient, just like regular gradient, is you have some kind of function, and it's not continuous, it's kind of discrete, so you only know integer points. It's like you only know pixels on an image. It's not a kind of a continuous image. Then in order to find, say, the slope here, we can approximate it by the slope using these 2 points. So basically, we find the difference between these 2 points, and then we divide it by the changing x value, which is exactly this formula here. And the main difference is we're not taking the limit when these 2 points are getting closer and closer. We're just going to use 1 to define the gradient of an image. So this will be our x gradient, and this will be our y gradient. And the way to compute them, they are actually very simple. So you don't actually need to know the formula that I showed you before. You just need to know the gradient is basically the pixel on the right subtracting the pixel on the left. So if you have an image with, say, 9 pixels, then the x derivative here is just this pixel value minus that pixel value. So it's a very simple definition. Why do we need this? It's because if you have an edge like a vertical edge here, then if you do right minus left, the value will be large if there is an edge, in particular vertical edge. If there's no edge, then they'll be similar, so the difference will be small. So it can be used to figure out whether this point is on a vertical edge or not on a vertical edge. Similarly, if we convolve it with a y gradient filter, then here, suppose we are at a horizontal edge, then this value minus this value will be, if it's large, actually here in absolute value, then it's an edge, it's a horizontal edge. If not, it's kind of flat here. And we are going to basically have a kind of fancy name, and we're going to call it Sobel filter. And it's the same as the derivative, but it's adding some weights in the nearby pixels in addition to the -1 and 1 here. So they are used to approximate the gradient of an image. So we will go back to this later. So one thing that's specific to multidimensional filters is that it's very slow to compute those. So it's actually faster if you convolve with one horizontal filter and then one vertical filter. It's easier compared to just convolve it with a two-dimensional filter. So what we're going to do is we get an image. We first convolve it with this one-dimensional filter like this, and we just move this around for each row, and then we get a resulting convolution, and then we convolve that convolved one with the vertical filter, and we just go through this column by column, and then we'll get the same thing as if we combine these two into a two-dimensional filter. Basically, we have like this, and just move this thing around. It turns out that it's slower to do this compared to doing these two separately. So what we do is we always want to decompose multidimensional here to two-dimensional filters into two one-dimensional filters, because that will be faster, a lot faster computationally. And in particular, this Sobel filter here can be decomposed into two parts. You do not need to know how to do this in general, and also you don't need to know how to combine two filters to make one two-dimensional filter, but you just need to know that some of these can be decomposed, so they'll be fast. And going back to the gradient of an image, you had two x gradient and y gradient, I mean x derivative and y derivative filters, which can be just the regular gradient filter or the Sobel filter. And then if you convolve it with the image, the resulting two images combined is called the gradient of the image. And of course, since these are vectors, so basically for each pixel there's a vector, and some of these vectors will point to different directions, and they'll have different lengths. So we are going to define the magnitude, which is just the length of the vector, and the gradient direction, which is which direction they're pointing to. Instead of showing you a diagram, let me actually show you how they work on an actual image. So suppose you have a 3x3 filter like this, and if it's identity, you will just give you the original image back. And if you try, say, the bottom Sobel filter, it will be basically the y derivative. And if you look at this, these are the y vertical, I mean horizontal edges. When you take the y derivative, you get the horizontal edges. And if you go back to the identity, you can see that these are actually horizontal edges in the image. And top and bottom, they are the same, except for it's going in the other direction. When you look at the image, it actually looks the same. And of course, you have left and right. So these are vertical edges, and right, these are also vertical edges. They are just in opposite directions. So it's either left minus right or right minus left. They are basically the same thing. Let's get back. Okay, so mathematically we had the first derivative, so of course we're going to have the second derivative. So remember, the second derivative is the Hessian matrix, and it's a matrix, so we don't want to deal with that. So we are going to just use the Laplacian. It's the thing that we will be interested in. Again, it's not clear why we are interested in these things, but in the next part, I will explain how they are used. So here, if you have taken calculus, I mean multivariate calculus, you should know that the Laplacian of a function is just the sum of the second derivatives. And there is a kind of a Newton approximation that's not clearly why there are like coefficients are like this. But again, you don't need to know these. You just need to know that how we are going to actually compute these for images. So here the coefficients are 1 minus 2, 1, and translating it into a filter, it becomes 1 minus 2, 1, and 1 minus 2, 1 in the other direction. If we sum them up, it becomes the Laplacian. So when you convolve whatever this is with the image, the resulting thing you'll get is the Laplacian of this image. And here I want to briefly talk about why we're using these things. So I mentioned this already, is that they can be used to find which pixels are edges in the image. So I will actually show you this later, because first I want to talk about the Gaussian filter. So images, they usually contain noise. So if you look at the image, there are like just strange weird dots, and we don't want all of these dots to be like small edges. Doesn't make any sense. So we want to remove those random noise. And the way to do this, well, of course, we're going to use another filter to do this. It's kind of a filter that makes the image more smooth, or make the function more smooth, if you think about the image as a two-dimensional function. So one such particular one is called the Gaussian filter, and it's often the one that's used to blur images, and also blurring means removing noise. And if you are familiar with the Gaussian random variable, the normal distribution stuff, you know that this is just a density function of a Gaussian random variable, but it's not important. Again, these things are not important. You don't need to know these. You just need to know how to compute it. And let's skip this. And if you actually look at a small Gaussian filter, a 3x3 one with a specific sigma value, it's just like a regular filter. So you can, what you can do is you can just substitute the numbers for S and T here, and then you will get each weight in the filter, which, well, it's not a useful exercise for you, so I will not talk more about it. And of course, the reason we're using this is because it can be decomposed into two one-dimensional Gaussian filter, which makes filtering very fast. And this is an example. And actually, if you compare this with the Sobel filter, they are actually similar. So what we have is basically Sobel filter is like first filtering. So first remove the noise and then compute the gradient. So if we have this, of course, we're going to do like the Laplacian with the Gaussian. So hopefully we get a fancy name. It turns out no, we are just calling these Laplacian of Gaussian, but we have a nice short version called the log filter, and it's basically the second derivative of the Gaussian function. And of course, the functional form is going to be crazy complicated, and we're never going to use this, because it turns out that this actually cannot be decomposed into two one-dimensional filters. So we never want to use this. So we're going to approximate it again. And the approximation is called the difference of Gaussian. And again, not a creative name, but a creative short version is called the dog filter. And in any case, it's just the difference between two Gaussian filters. It turns out it's very close to the Laplacian of Gaussian. So we're going to use these two Gaussian filters and combine them to make the Laplacian of Gaussian, because each of these can be decomposed into one-dimensional filters. So of course, this will be faster. Instead of drawing a diagram, let me actually load one. This one is a good one, but it's too small. So a log filter in 2D, the continuous version looks like this. So in 1D, it looks like that. In particular, what we're doing here is we would have a very thin and tall Gaussian filter, and we have a bigger Gaussian filters in the other direction. If we take the difference between the two, then we will get a shape that's approximating this shape. And it turns out it's actually very close to this Laplacian of Gaussian filter. So we're going to use dog to approximate log. So I promised you that I will show you how to find edges in an image. So let's go to the other website here. So here you have an image of a, this is not panda. What is it? It's called panda, but I think small panda. Oh, well, whatever. But if you have an image, you want to find the edges in the image. So the first thing, as I said, is you need to use Gaussian filter to filter through the image. And let's actually compare these. The original image is kind of not blurred, and if you apply the Gaussian filter, it becomes blurred. So some of the noises will be removed. And then the next thing is find the derivative gradient in x, and also find the gradient in y. And then you can do the sum of square and the square root. You get the magnitude, and magically it looks like parts of the edge already. So basically, the pixels that have very high values of the magnitude of gradient, they are corresponding to both the x direction edges and the y direction edges. So combining them, it will actually highlight the edges in the image. Of course, we need to do something extra. There are too much of these like low value edges. We need to remove those. And also, it seems that these are like regions, not curves or lines. So the first thing we're going to do is to put like remove the regions that are edges and make it like a curve. So that part is called non-maximum suppression. So basically, if you have an edge that's not a local maximum, basically means it's close to another edge that's stronger, we're going to remove it. So if you look at this, it's actually better. So they're like thinner lines. So we only keep the highest valued edges after this step. And now we have those kind of weaker edges. They are edges, but they are not like very clear edges. So we're going to have the last step called hysteresis threshold. Basically, it's a fancy word for just you use a threshold. Any edge that's weaker than this threshold, I mean, having a smaller magnitude of gradient than that threshold value, they will be removed. And also all the edges that are connected to those will be removed as well. So after I remove all of these and then highlight the remaining edges, they will actually look like the edges in this image.